There is another computer simulation method which is called Monte Carlo simulation. I will go to the next slide, which is called Monte Carlo simulation. So, this is another simulation technique which is quite popular, and this simulation method is also very useful to generate the different microstructures of your system. So, I will briefly touch upon Monte Carlo simulation, and here I will specifically look at the Metropolis Monte Carlo algorithm, Metropolis algorithm, which will guide us how to generate new conformations, new microstructures of a system. So, in the Metropolis algorithm, there are 4 important steps. So, Metropolis algorithm. So, as I said that we are now trying to generate new conformation of my system of interest by Monte Carlo simulation technique. So, and under that, Metropolis algorithm is a very popular algorithm to generate new conformation. So, in Metropolis algorithm or in Monte Carlo simulations, the new conformations of the system is generated by using random number generator, and that's a big difference of Monte Carlo with molecular dynamics. In molecular dynamics simulations, we generated the new conformations by solving Newton's equation of motion, Newton's second law. We solved equation of motion to generate new conformations, whereas in Monte Carlo simulation, we will be generating the new conformation of my system by using random number generator. So, in Metropolis algorithm, as I said, there are important 3 steps. So, in step 1, what I will do, I will generate a new set of coordinates of my system randomly using random number generator. So, if x new, y new and z new are the new coordinates of ith particle, I will generate, I will obtain x new, y new, z new from my old conformation. So, in Metropolis algorithm, we will be generating the new coordinates of ith particle using random number generator. So, let us say x new, y new and z new are the x, y, z coordinates of my ith particle, and this x new, y new and z new I will get as follows. So, x old is the coordinate of the ith particle, and 2 zeta, okay, I will write zeta a little better, zeta minus 1 del r max, where my zeta is a random number generator. It is a random number, not generator, random number. Likewise, I will get y new from y old and by using a random number, and delta r max is the maximum displacement given to the particle. So, z new similarly depends on z old plus 2 zeta minus del r max. So, as you see here, so x new, y new and z new we are generating using the random number zeta. So, this zeta random number will be between so this random number you can use different function available in a computer. Usually there is a library called random function, RANF, and this random number basically generate numbers between 0 and 1. So, with this random number generator, we will randomly create new set of coordinates for my system, and that will give me a new conformation. So, that was my step 1. In step 2, I will calculate the potential energy of the system. Let us say my calculated potential energy of the system is U nu. Okay, I'll use a different, sorry. So, in the new step, I'll calculate the new energy of the system, and let's say that energy is E nu. So, I'll compare this E nu. So, calculate E nu. So, step 2 is calculate energy of the system, and which is E nu. Calculate E, which we say the E nu. In step 3, I compare E nu with my energy in the previous step. If E nu is less than E old, where old is basically the energy of this configuration and E nu is the energy of this configuration. If E nu, which is a new conformation, is having lesser energy than the older configuration, then I accept this configuration or accept this microstructure. In step 4, if my E nu is greater than epsilon old, I accept it with certain probability. I do not discard it completely. So, this is meaning my energy is a fill. Energy is a fill. So, if energy is a fill, I accept this new configuration with the following probability. So, I calculate probability of the new, and this is my old, and I basically calculate the Boltzmann factor, which is exponential minus epsilon n minus epsilon old. That is what I used, I suppose, new and old. I calculate this Boltzmann factor. I calculate this Boltzmann factor, and if my random number, so my random number is between 0 to 1, and then I compare this Boltzmann factor e to the power minus E nu minus E old divided by kBt. I compare with this. If this is valid, I accept this. Why I accept if this condition is fulfilled? So, this is valid only when my epsilon nu is not too big. If epsilon nu is just little bigger than epsilon old, then what will happen? So, this difference is close to 0, and then this whole Boltzmann factor is 1. So, this is fulfilled, that because 1 is more than any number between 0 to 1. So, I accept it. If my E nu is very large than E old, then this Boltzmann factor becomes close to 0, and this condition does not fulfill. So, I do not want to get a configuration which is having a much higher energy than the previous configuration, because I am having very high and higher energy configuration, and I do not know whether that is a good configuration or not. On the other hand, if I generate a configuration which is having energy just little more than my previous configuration, I tend to take that. So that you know, I always may not go in my energy profile below. I might have small energy barrier, and then I might go to a better energy state. So, I should not just get trapped in this local minima. I should take up some configuration which will allow me to cross this barrier and can get to a better conformation. So, this is my free energy profile with reaction coordinate. Okay, so that's the Monte Carlo simulation. Here one thing I need to stress is that when I'm generating the new conformation, I am trusting, or I am using only the preceding step. I am generating new configuration only based on my preceding configuration. I do not care what was the configuration before X old, and that is where Monte Carlo and molecular dynamics differ. So, if I compare molecular dynamics and Monte Carlo, so first difference, the most important difference is in MD we solve Newton's, we basically look at Newton's equation of motion, and so we solve Newton's second law by solving equation of motion, whereas in Monte Carlo we generate the new configuration by random number. So, we use the random number generator to generate the configuration randomly. And the second difference between MD and MC is that here there is a time information. There is a time information because we are solving force is equal to mass into acceleration, and the acceleration is having the time information, and therefore, there is a time information present in MD. Whereas in Monte Carlo simulation, our new configuration is depending only on the preceding step, and it does not have any memory. What was the configuration before the preceding step, and that's called the Markov chain model. So, in Monte Carlo there is no history. There is no history, and that is it follows the Markov chain model. Nevertheless, both the MD and MC simulation techniques help you, which I'm emphasizing again, is that these techniques basically help you to generate your ensemble. It basically helps you to get all possible microstates of your system, so that you can calculate the thermodynamic properties in the accurate level which matches the experimental data. So, both MD and MC are generating lot many microstates, and when you put up this information on the microstates, you see the time evolution. When you are talking about MD, there is no time evolution from MC, but ultimately when you take the average or this ensemble, you get the property which you can compare with experimentally measured property, which are the macrostates.